Hello, in this lecture I will answer two questions. On both questions we will find out the area of a shaded region. We'll start with the first question. In the drawing we have three semicircles. This is the biggest semicircle. It contains those two smaller semicircles. You know that the radius of this semicircle equals to 2 units in its length. The radius of this small semicircle is equal to 1 unit in its length. Again, our task is to find out the size of this shaded area. So first of all, we define the center of the biggest semicircle. This semicircle, this point is point O. We define the radius of this biggest semicircle as x. We define the center of this semicircle. This point is point P. We define the center of this small semicircle. This point is point Q. We define the point of tendency of tangent AB with this semicircle. This point is point M. And finally, we define the point of tendency of tangent AB with this semicircle. This point is point N. So here we can implement rule 1, because we have the radius PM of this semicircle is equals to x. The radius PM is drawn to point M, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QN of this small semicircle. The radius QN is equals to 1. The radius QN is drawn to point N, that is the point of tendency of tangent AB with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. Those two small semicircles have external lines between them at this point. That is to say, they touch each other externally at this point. So we define the attaching point. This point is point T. And whenever you have an external line between two circles or semicircles, you can implement rule 10 in the drawing. Repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. In the drawing, we have those two circles that touch each other externally at this point, point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the centers together is of course the straight line OM, and this straight line OM, according to this rule 10, this straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. So can we implement rule 10 in our drawing? In our drawing, those two small semicircles have an external line between them at point T. The center of this semicircle is at point P. The center of this small semicircle is at point Q. The third line that connects the circles together is of course the third line PQ. According to rule 10, the third line PQ must pass from point T, that is their touching point. Or PTQ is one side line. Again, PTQ is one side line according to rule 10. So we join points P and Q together by side line, and according to rule 10, the third line PQ must pass from point T, that is their touching point. As you can see from the drawing, indeed the thread line PQ that connects the circles together passes from point T, that is their touching point, exactly according to rule 10. So, because of the fact that PTQ is one side line, it means that PQ must be equal to PT plus TQ. So PQ in total equals to PT. PT is the radius of this semicircle, equals to 2. Plus TQ. TQ is the radius of this small semicircle, that equals to 1. Okay, again, that because of the fact that PTQ is one side line, it means that PQ equals to PT plus TQ. That is to say, PQ equals to 2 plus 1, that is 3. So PQ equals to 3 in itself according to rule 10. In the next step, I'll copy this coordinate PQ and M in a new page, and we'll do a construction on the new drawing. After I copy this coordinate PQ and M in a new page. Actually, this is coordinate PQMM that I copied from the original drawing. In the next step, we'll do a construction, that is to say from point Q, we'll draw perpendicular on PM. Again, from point Q, we'll draw perpendicular on PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and PM. This point is point L. So actually, by doing this construction, we created the small quadrangle LQ and M. Inside this small quadrangle LQ and M, we have 1, 2, 3 right angles. And therefore these 4 pieces again must be equal to 90 degrees in each side, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in this small quadrangle LQ and M, we have 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this small rectangle LQ and M, side QN equals to the opposite side LN. But QN equals to 1, and therefore the opposite side LM must be also equal to 1 unit in its length. So LM equals to 1. What is the length of this missing line segment PL? From the drawing it is very easy to see that PL equals to PM minus LM. PL equals to PM minus LM. So PL in total equals to PM. PM is 2 minus LM. We just write down formula that LM equals to 1. So total PL equals to 2 minus 1, that is 1. PL equals to 1 unit in its length. In the next step, we will implement the Pythagoras theorem on this small right green triangle PLQ. Here by PT is the permission for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This right triangle PLQ, PQ is the hypotenuse, so PQ square, that is the square of the hypotenuse, is equal to PL square plus LQ square. PQ is 3, therefore PQ square is 3 squared, that is 9, and it is equals to PL square. PL is 1, therefore PL square is 1 squared, that is 1, plus LQ square. LQ is the missing side, so we leave it as it is, so it is LQ square. So in total, found out that according to the Pythagoras theorem, this green triangle PLQ, 9 equals to 1 plus LQ square. Here we subtract 1 from this equation, and we get that 9 plus 1 is 8 equals to LQ square. So LQ square equals to 8. Here we substitute we substitute 8 by 4 times 2. So 4 times 2 equals to LQ square. Here we take a root out of this equation, and finally get that LQ, let me see, side LQ is equal to the square root of 4 is 2. So inside the root we left only with 2. So in total we found out that the length of this line segment LQ is equal to 2 times square root of 2 units in its length. But we also know that the opposite sides of a rectangle are equal to each other. So in this form of LQ and M, side LQ must be equal to the opposite side MN. But LQ is 2 times square root of 2, and therefore the opposite side MN must be also equal to 2 times square root of 2 units in its length. So we found out that this is line segment MN, this equals to 2 times square root of 2 units in its length. In the next step, we define the length of this short line segment MO as A. So what is the length of this missing line segment ON? ON or NO equals to NM minus OM. Write it down. Line segment NO in total is equal to NM minus OM. So NO equals to NM. NM is 2 times square root of 2 minus OM. OM equals to A. So total, if you found out that line segment NO equals to 2 times square root of 2 minus 1 units in its length. This is line segment ON that is equals to 2 times square root of 2 minus A units in its length. Point O is the center of this biggest semicircle. So in the next step, we will join points O and Q together by straight line. Again, point O is the center of this biggest semicircle. Point Q is the center of this small semicircle. EF is the diameter of this small semicircle. The radius of this small semicircle equals to 1, and therefore the diameter EB equals to 2, of course. The diameter EF of this small semicircle equals to 2 units in its length. And this is line segment OQ that bisects chord EF. Again, line segment OQ bisects chord EF. Why OQ bisects chord EF? Because point Q is the midpoint of chord EF. It is actually the center of this small semicircle. OQ bisects EF because the first half of EF is EQ and the second half of chord EF is QB. Each of them is equal to 1. So we should find out that line segment OQ, that is one from the center of this biggest semicircle, that is point O. Line segment OQ bisects chord EF. It divides chord EF into 2 halves. The first half EQ is 1, the second half QF is also 1. Repeat again. This is line segment OQ that is one from the center of this biggest semicircle, that is actually point O. Line segment OQ bisects chord EF. And whenever you have a line segment that is drawn from the center of the circle or a semicircle and bisects the chord, then that line segment OQ will be also perpendicular to chord EF, according to Rule 30. Rule 30. According to Rule 30, a line segment that is drawn from the center of a circle and bisects the chord will be also perpendicular to that chord. In the drawing, we have a circle. Point O is the center of this circle. This is line segment OM that is drawn from the center of this circle, that is actually point O. Line segment OM bisects chord AB. Again, line segment OM bisects chord AB according to our construction. And therefore, according to this Rule 30, line segment OM that bisects chord AB, line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this Rule 30. So you can actually implement Rule 30 in our drawing. I put in our drawing from the center of this biggest semicircle that is actually point O. We have line segment OQ that by itself code EF, and therefore according to rule 30, line segment OQ will be perpendicular to code EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to rule 30. So in the next step, we will join points O and E together by a straight line. What is the definition of line segment OE? Line segment OE starts from the center of this biggest semicircle, that is point O, and ends at point E, that is the point of the biggest semicircle itself. So this is exactly the definition of a radius. Therefore, OE is the radius of this biggest semicircle, that equals to x according to our definition. So OE equals to x. In the next step, we will implement the Pythagoras theorem on this green right line EQO. Again, we will implement the Pythagoras theorem on this green right line EOQ. So here by PT is introduction for Pythagoras theorem. So in this green right line EQO, according to the Pythagoras theorem, EO squared, that is the square of the hypotenuse, is equal to EQ squared plus QO squared. And again, in this right triangle EQO, according to the Pythagoras theorem, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EO is x, therefore EO squared is x squared. And it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1 plus QO squared. QO is one side of this green right triangle QO, but QO is also the hypotenuse of this right triangle QNO. Repeat again, QO is also the hypotenuse of this pink right triangle QNO. So we'll implement the Pythagoras theorem on this pink triangle QON, and get that according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse of this pink triangle, equals to QN squared plus NO squared. And again, in this pink triangle QON, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So in total, if we found out that EO squared equals to EQ squared plus QO squared. EO is x, therefore EO squared is x squared, it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1 plus QO squared. QO is the hypotenuse of this pink triangle QNO, therefore QO squared equals to QN squared plus NO squared. So QO squared equals to QN squared plus NO squared. So in total, we found out that x squared, according to equation 1, x squared equals to 1 plus NQ squared, or QN squared. QN is also 1, therefore QN squared is 1 squared, that is 1 plus NQ squared, plus NO squared. NO is 2 times square root of 2 minus a, therefore n whole square is 2 times square root of 2 minus a square. So in total, according to equation 1, we actually found out that x squared equals to 1 plus 1 plus 2 times square root of 2 minus a square. So according to equation 1, x squared equals to 1 plus 1 is 2 plus we have 2 times square root of 2 minus a square. So we'll open the brackets of this expression and we get that 2 times square root of 2 minus a square equals to 2 times square root of 2 squared, that is 8, plus a square minus 2 times square root of 2 times a. So in total, we found out that according to equation 1, x squared equals to 2 plus 8 is 10. We have here minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times a. So in total, according to equation 1, we found out that x squared equals to 10 minus 4 times square root of 2 times a plus a squared. And again, according to equation 1, x squared equals to 10 minus 4 times square root of 2 times a plus a squared. We will repeat on the same process that we did on the side of this big semicircle on the other side here. That is to say, we will join points O and P together by straight line. Point O is the center of this biggest semicircle. Point P is the center of this semicircle. So PC is the radius of this semicircle. This equals to 2. Likewise, PD is also the radius of this semicircle. This equals to 2. So CD of this is the diameter of this semicircle. The diameter CD equals to 4. So point P is the midpoint of the diameter CD. It is the center of the circle. It is the midpoint of the diameter CD. It is actually the midpoint of chord CD. So it's point P, line segment OP, bisect chord CD, it's point P. Again, line segment OP, bisect chord CD, it's point P. That is to say, it divides chord CD into two halves at point P. The first half CP is 2, the second half PD is also 2. So it's point P, line segment OP, bisect chord CD. And whenever you have a line segment that is drawn from the center of the circle and bisect the chord, that line segment will be also perpendicular to that chord. Because of the fact that OP bisects chord CD, OP also will be perpendicular to chord CD according to rule 30. If OP is perpendicular to CD, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size. We just implemented rule 30 in our drawing. We have line segment OP that is drawn from the center of this circle, that is point O, that bisects chord CD. And therefore, according to rule 30, line segment OP must be also perpendicular to CD. If OP is perpendicular to CD, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. So in the next step, we will join points O and C together by straight line. Point O is the center of this biggest semicircle. Point C is the point of the biggest semicircle itself. Therefore, OC is the radius of this biggest semicircle. Is equals to X. So repeat on the same process as we did on this side of this biggest semicircle. We'll implement the Pythagoras theorem on this right triangle CPO. Again, we'll implement the Pythagoras theorem on this right green triangle CPO. So according to the Pythagoras theorem, in this on this green triangle CPO, CO squared, that is the square of the hypotenuse, equals to PC squared plus PO squared. And again, in this triangle CPO, according to the Pythagoras theorem, CO squared, that is the square of the hypotenuse, equals to PC squared plus PO squared. CO is X, therefore CO squared is X squared. And it is equal to CP squared. CP is 2, therefore CP squared is 2 squared, that is 4, plus PO squared. PO is one side of this green right triangle CPO, but PO is the hypotenuse of this pink triangle PMO. Again, PO is also the hypotenuse of this pink triangle PMO. So we will implement the Pythagoras theorem on this pink triangle POM, and we get that according to the Pythagoras theorem, PO squared, this is the square of the hypotenuse of this pink triangle PMO, PO squared equals to PM squared plus MO squared. Repeat again. PO is also the hypotenuse of this pink triangle PMO, and therefore according to the Pythagoras theorem, on this pink triangle POM, PO squared equals to PM squared plus MO squared. Again, CO squared equals to C squared plus PO squared. CO is X, therefore CO squared is X squared, and it is equals to PC squared. PC is 2, therefore PC squared is 2 squared, that is 4. We have PO squared. PO is the hypotenuse of this pink triangle PMO, and therefore PO squared equals to PM squared plus MO squared. Again, PO squared equals to PM squared plus MO squared. So in total, according to equation 2, we should find out that X squared equals to 4 plus PM squared. PM is 2, therefore PM squared is 2 squared, that is 4 plus MO squared. MO is A, therefore MO squared is A squared. So in total, according to equation 2, we should find out that X squared equals to 4 plus A squared. According to equation 2, X squared equals to 4 plus 4 is 8 plus A squared. And again, according to equation 2, I should find out that X squared equals to 8 plus A squared. This is according to equation 2, and according to equation 1, we have only found out that X squared equals to 10 plus A squared plus 4 times square root of 2 times A. So we have two different equations for X squared. Therefore, we get equation 3 that states that x squared according to equation 1 must be equal to x squared according to equation 2. X squared according to equation 1 equals to 10 plus a squared minus 4 times square root of 2 times a, and it must be equal to x squared according to equation 2. X squared according to equation 2 equals to 8 plus a squared. So in total according to equation 3 we actually found out that 10 plus a squared minus 4 times square root of 2 times a equals to 8 plus a squared. So here we have a squared on both sides of this equation, so a squared gets cancelled. After we cancel a squared, we subtract 8 from this equation, equation 3, and finally get it according to equation 3. 10 minus 8 is 2, so 2 minus 4 times square root of 2 times a equals to 8 minus 8 is 0. So 2 minus 4 times square root of 2 times a equals to 0. Here we add 4 plus square root of 2 times a to this equation. And we get that 2 equals to 4 times square root of 2 times a. Here we divide this equation, equation 3 by 2, and finally get that according to this equation, equation 3, 2 over 2 is 1, and 4 over 2 is 2. So in total, in this side of the equation, we have 2 times square root of 2 times square root of 2 times a. So in total, according to equation 3, we actually found out that 1 equals to 2 times square root of 2 times a. Here we divide this equation, equation 3 by 2 times square root of 2, and finally get that according to equation 3, a equals to 1 over 2 times square root of 2 units in its term. Okay, this is my assignment m1 is equals to a, and a equals to 1 over 2 times square root of 2 units. According to equation 2, we found out that x squared equals to 8 plus a squared. So x squared equals to 8 plus a squared. A is 1 over 2 times square root of 2, and therefore a squared must be equal to 1 over 2 times square root of 2 squared, that is 8. So in total, according to equation 2, we actually found out that x squared equals to 8 plus 1/8. So x squared equals to 1/8 plus 8. So here we multiply 8 by 8 and then we divide it by 8 in order to overcome factor with this number, and get that we have 1/8, since 8 times 8 is 64 divided by 8. We multiply 8 by 8 and then we divide 8 by 8, so we change nothing. So in total, we should found out that x squared equals to 64 plus 1 is 65 over 8. So according to equation 2, we actually found out that x squared equals to 65 over 8. Our task is to find out the size of this shaded area. So, what is the size of this shaded area? From the drawing, there is to see that the size of this shaded area in total equals to the area of this biggest semicircle minus the area of this right semicircle minus the area of this left semicircle. And again, the size of this shaded area in total must be equal to the area of this biggest semicircle minus the area of this right semicircle minus the area of this left semicircle. So, write it down. If you found out that the size of this shaded area, the area that we are looking for in this question. In total, it is equals to the area of this biggest semicircle minus the area of this right semicircle minus the area of this left semicircle. And again, the size of this shaded area in total equals to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. What is the area of the biggest semicircle? What is the area of this biggest semicircle? We know that the radius of this biggest semicircle is x, and therefore the area must be equal to pi x squared over 2. So the area of the biggest semicircle equals to pi x squared over 2. That is the area of the circle over 2. The radius is x, and therefore the area of the circle is pi x squared. And if we divide it by 2, we get the area of this biggest semicircle minus the area of this right semicircle. We know that the radius of this right semicircle is 2, therefore the area must be equal to pi 2 squared over 2. It's minus pi 2 squared over 2. Minus the area of this left semicircle. The radius of this left semicircle is 1, and therefore the area must be equal to pi 1 squared over 2. So in total, we found out that the size of the shaded area equals to pi x squared minus pi 2 squared over 2 minus pi 1 squared over 2. So here we take pi over 2 as a common factor out of those three expressions. So inside the brackets we left here with x squared minus 2 squared is minus 4 minus 1 squared is minus 1. So in total we found out that the size of the shaded area equals to pi over 2 times x squared minus 4 minus 1. So it is pi over 2 times x squared. X squared is 65 over 8. Minus 1 minus 4 is minus 5. So in total the size of the shaded area equals to pi over 2 times 65 over 8 minus 5. Here we will multiply minus 5 by 8 and then we divide it by 8 in order to have a common factor with this number. And you get that the size of the shaded area in total equals to pi over 2. We have here 65 over 8. We multiply minus 5 by 8. Minus 5 times 8 is minus 40. And then we divide it by 8, so we change nothing. So in total, the size of the shaded area equals to pi over 2. 65 minus 40 is 25 over 8. So in total, we found out that the size of the shaded area equals to, in the numerator of this expression, we have 25 pi over 2 times 8 is 16. 25 pi over 16, in total it is equal to 4.908 square units in size. Repeat again, and we found out that the size of this shaded area in total it is equal to either 25 pi over 16 square units in size. So in terms of numbers, the size of this shaded area is equal to 4.908 square units in size. Okay, so finish with the first question. In the next step, I present you the second question and solve the second question of this lecture. In the second question, our task is to find out the size of this shaded region. The shaded region is this small semicircle. So we have to find out the area of this small semicircle, that is the shaded region. So in the drawing, we have two semicircles that intersect with each other. This is line 7 AM, this equals to 3 units in center. This is line 7 MN or code MN, that is also equals to 3 units in its length. This is line 7 NB, this equals to 2 units in its length. Again, our task is to find out the size of this shaded area, and it's actually the size of this small semicircle. So AB is the diameter of this big semicircle. AB in total equals to AM, that is 3, plus MN, that is also 3, plus NB, that is 2. So in total, the diameter AB of this big semicircle equals to 3 plus 3 plus 2, that is 8. So AB, the diameter AB of the big semicircle, is equal to 3 plus 3 plus 2, that is 8. So the diameter AB equals to 8. We define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. So it is 8 over 2, that is 4. So the radius R of this big semicircle is equal to 4 units in its length. We define the center of this big semicircle, this point is point O. We define the center of this small semicircle, this point is point S. What is the length of this line 7? Line 7 MO. From the drawing, it is very easy to see that MO equals to AO minus AM. So MO in total equals to AO, that is the radius of this big semicircle, that is 4, minus AM. AM is 3. So in total, you should find out that MO equals to 4 minus 3, that is 1. So MO equals to 1 unit in its length. In the next step, we will do a construction, that is to say, from point S, that is the center of this small semicircle, we will do perpendicular on chord MN. Again, from point S, that is the center of this small semicircle, that is the center of this small semicircle, we will do perpendicular on chord MN. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and called MN. This point is point T. We define the length of perpendicular ST as H. So what we did here, from point S, that is the center of this small semicircle, we draw perpendicular ST on chord MN. And whenever you draw a perpendicular from the center of the circle or semicircle towards any chord, it will bisect the chord, according to rule 15. So perpendicular ST bisect chord MN. Again, perpendicular ST bisect chord MN, according to rule 15. And please click on rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord bisects the chord. In the drawing, we have a circle. Point S is the center of this circle. This is perpendicular ST and chord MN. Again, according to our construction, we draw perpendicular ST and chord MN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 15, perpendicular ST bisects chord MN. Again, perpendicular ST bisects chord MN. If ST bisects chord MN, it means that MT equals to TN, and the first half MT equals to the second half TN, and each half must be equal to MN over 2 because MN has been bisected. So we can implement rule 15 in our drawing. In our drawing, we have from the center of this small semicircle, that is to say from this point S, we have perpendicular ST on chord MN. According to rule 15, perpendicular ST bisects chord MN. If ST bisects chord MN, it means that the first half MT must be equal to the second half TN, and each half must be equal to MN over 2. So, okay, now, perpendicular ST bisects chord MN, and therefore, according to rule 15, the first half of chord MN is MT, and it must be equal to the second half of chord MN, that is Tn, and each half must be equal to Mn over 2 because Mn has been bisected by St. Okay, again, according to rule 15, perpendicular ST bisects chord Mn. So the first half MT must be equal to the second half Tn, and each half must be equal to Mn over 2 because Mn has been bisected. Mn is 3, therefore Mn over 2 is 3 over 2, that is 1.5. So Mt equals to Tn equals to 1.5 units. So the first half of chord Mn is Mt, that is 1.5 units. And it is equals to the second half of chord Mn, that is chord Tn, that is 1.5 units also. Again, Mt equals to 1.5, and Tn also equals to 1.5 units in its length, according to rule 15. In the next step, we will join points O and S together by straight line. Point O is the center of this big semicircle. So from point O, that is the center of this big semicircle, we draw line segment OS. Point S is the center of this small semicircle. SP is the radius of this small semicircle. We define the radius of this small semicircle as X. So SP is the radius of X. Likewise, SQ is also the radius of this small semicircle. That is equal to X according to our definition. So from the center of this big semicircle, that is to say from this point O, we draw line segment OS that bisects chord PQ. Why OS bisects chord PQ? Because PQ is the diameter of this small semicircle, that in total it is equal to 2x. The diameter PQ or chord PQ has been bisected by OS into two halves. The first half PS is x, the second half SQ is also x. So whenever you have a line segment that is drawn from the center of the circle and bisects a chord, then that line segment will be also perpendicular to that chord. Because of the fact that OS bisects chord PQ, OS will be perpendicular to PQ. Again, because of the fact that OS bisects chord PQ, OS will be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. Okay, again, because of the fact that line segment OS bisects chord PQ, line segment OS will be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. In the next step, we define the length of line segment SO as Y. And we will implement the Pythagoras theorem on this right triangle, but before that we will find out the length of this short line segment OT. What is the length of OT or TO? From the drawing it is very easy to say that TO in total equals to TM minus OM. So TO equals to TM is 1.5. Minus OM is 1. So in total we should find out that TO equals to 1.5 minus 1, that is 1 half. So TO equals to 1 half units in its length. TO equals to 1 half units in its length. In the next step, we will implement a Pythagoras theorem on this right triangle SOT. So we copy triangle SOT in the equation. We will implement on it the Pythagoras theorem. We again implement the Pythagoras theorem on this right triangle SOT. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle SOT that I copied from the original drawing. In this right triangle SOT, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle SOT, SO squared, that is the square of the hypotenuse, is equal to ST squared plus OT squared. SO is y, therefore SO squared is y squared, and it is equal to ST squared. ST is h, therefore ST squared is h squared, plus OT squared. OT is 1 half, therefore OT squared is 1 half squared, that is 1/4. So in total, according to equation 1, we actually found out that y squared equals to h squared plus 1/4. In the next step, we will join points S and N together by a straight line. Point S is the center of this small semicircle. Point N is the point of the small semicircle itself. Therefore, Sn is the radius of this small semicircle. Is equals to x. So in the next step, we will implement the Pythagoras theorem on this right triangle STN. So copy triangle STN in your page, and we will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Side Tn of this triangle STN equals to 1.5 units in its length, or 3/2, 3 halves. So actually, this is the right triangle STN that I go to on the original drawing. In this right triangle STN, according to the Pythagoras theorem, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn is x, therefore Sn squared is x squared, and it is equals to st squared. St is 8, therefore st squared is 8 squared plus tn squared. Tn is 3 halves, therefore tn squared is 3 halves squared, that is 9 quarters. So in total, according to equation 2, x squared equals to x squared plus 9 quarters. This is according to equation 2. According to equation 1, we already found out that y squared equals to x squared plus 1 quarter. So we have here two equations. So we subtract those two equations from each other. So we get equation 2 minus equation 1. So it is x squared minus y squared equals to this side of the equation 2 we have x squared plus 9 quarters minus equation 1. In this side of this equation 1 we have x squared plus 1 quarter. In total, if you found out that according to equation 3, x squared minus y squared equals, here we open the brackets, equals to x squared plus 9 quarters. We'll open the brackets here, and get it, after open the brackets, we have here x squared minus 1 quarter. So in total, according to equation 3, we actually found out that x squared minus y squared equals to 8 squared minus 8 squared is 0. 9 quarters minus 1 quarter is 8 quarters. 8 quarters is 2. So in total, if you found out that x squared minus y squared equals to 2. This is according to equation 3. X squared minus y squared equals to 2. In the next step, we will join points P and O together by straight line. What is the definition of line segment OP? Line segment OP starts from the center of this big semicircle and ends at point P, that is the point of the big semicircle itself. Therefore, this is exactly the definition of a radius. Therefore, OP is the radius of this big semicircle, that is equals to 4 units in its length, according to what we already found out in the beginning of the lecture. So OP equals to 4 units in its length. In the next step, I will copy the right triangle OSP in a new equation. We will implement on it the Pythagoras theorem. So actually, this is the right triangle PSO that comes from the original domain. In this right triangle PSO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PS squared plus SO squared. Okay. PO is 4, therefore PO squared is 4 squared, that is 16, and it equals to PS squared. PS is x, therefore PS squared is x squared plus SO square. SO is y, therefore SO square is y square. So in total, according to equation 4, we actually found out that x square plus y square equals to 16. This is according to equation 4, while according to equation 3, we only found out that x square minus y square equals to 2. And again, we have here two equations. According to equation 4, x squared plus y squared equals to 16, while according to equation 3, x squared minus y squared equals to 2. Here, we let equation 4 to equation 3, we let those two equations with each other. And we get that x squared plus x squared is 2x squared, y squared minus y squared is 0, and it is equals to 16 plus 2, that is 18. So in total, according to equation 5, we actually found out that 2x squared equals to 18. Here we will divide this equation 5 by 2, and finally get that according to equation 5, x squared equals to 18 over 2 is 9. So x squared equals to 9. Our task is to find out the size of this shaded area. So I mentioned before, the shaded area it is actually this small semicircle. So we have to find out the area of this small semicircle, that's actually the size of this shaded area. So the size of the shaded area it is actually the area of this small semicircle, and because of the fact that the radius of this small semicircle is x, therefore the area of this small semicircle must be equal to pi x squared. Pi x squared over 2, of course. So the size of the shaded area is equal to pi x squared over 2. So it is pi over 2 times x squared. We just now found out that x squared equals to 9. So the size of x squared by 9. So in total we found out that the size of the shaded area equals to 9 pi over 2. 9 over 2 is 4.5 times pi. So the size of the shaded area it is equal to either 4.5 pi square inch in size, or in terms of numbers it is equal to 14.137 square inch in size. Okay, again I should find out that the area that we are looking for in this question, that is the area of this shaded region, is equal to either 4.5 pi square inch in size, or in terms of numbers it is equal to 14.137 square inch in size. So we finished to answer the second question. In the next step, as far as the lecture, we start with the first question. We repeat on the solution of the first question, and then we repeat on the solution of this second question. In the first question, our task was to find out the size of this shaded region. So in the drawing, we have 3 semicircles. This is the biggest semicircle that contains those 2 smaller semicircles. We know that the radius of this small semicircle equals to 2 units in itself, the radius of this small semicircle equals to 1 unit in itself. Again, our task is to find out the size of this shaded region. So first of all, we define the center of this biggest semicircle, this point is point O. We define the center of this semicircle, this point is point P, and define the center of this semicircle, this point is point Q. Likewise, we define the point of tendency of tangent AB with this semicircle, this point is point M, and we define the point of tendency of tangent AB with this semicircle, this point is point N. Here we can implement rule 1, because we have the radius PM that is equals to 2, the radius PM is drawn to point M, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius Qn that equals to 1, the radius Qn is drawn to point N, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Because of the fact that those two circles touch each other externally at point T, we can implement rule 10. On page clicking on rule 10, according to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing, we have those two circles that touch each other externally at this point, point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects their centers together is, of course, the straight line OM. And this straight line OM must pass through point P, this is their touching point. Or OPM is one straight line. Again, OPM is one straight line according to this rule, rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing, those two semicircles have an external arch between them at this point T. The center of this semicircle is at point P. The center of this small semicircle is at point Q. The straight line that connects the centers together is, of course, the straight line PQ. And this straight line PQ must pass through point T, this is their touching point. Or PTQ is one side line. Again, PTQ is one side line according to rule 10. If PTQ is one side line, it means that PQ in total must be equal to PT plus TQ. So PQ equals to PT. PT is the radius of this semicircle, that is 2, plus TQ. TQ is the radius of this small semicircle, that is 1. So in total, according to rule 10, PQ must be equal to 2 plus 1, that is 3. So PQ equals to 3 units in its length according to rule 10. In the next step, I complete the quadrangle P, Q, and M in a new page and analyze the new drawing. Actually, this is the quadrangle P, Q, and M. This is according to the original drawing. We already found out that PQ equals to 3 according to rule 10. PM is the radius of the medium semicircle that equals to 10, and Qn is the radius of the smallest semicircle that equals to 1. Mn is the only missing side. So here we did construction in this quadrilateral PQ and M. From point Q we do perpendicular on PM. Again, from point Q we do perpendicular on PM. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and PM. This point is point L. By doing this construction, we created here the small quadrilateral LQ and M. In this small quadrilateral LQ and M, we have 2 right angles, and therefore this 4 pieces angle must be equal to 90 degrees in size. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 pieces angle must be equal to 90 degrees in size. So in quadrilateral LQ and M, we have 4 right angles, and therefore it is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in rectangle LQ and M, side QN must be equal to the opposite side LM. But QN is 1, therefore the opposite side LM must be also equal to 1 unit in its length. What is the length of this piece in line segment LP? LP equals to LM, LP equals to PM minus LM. So PL equals to PM minus LM. So PL equals to PM, that is 2, minus LM, that is 1. So in total, PL equals to 2 minus 1, that is 1. So PL was 1 unit in its length. In the next step, we implemented the Pythagoras theorem on this right triangle PQL. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendicular. So in the right triangle P, this right triangle PQ squared, this is the square of the hypotenuse, equals to PL squared plus LQ squared. PQ is 3, therefore PQ square is 3 squared, that is 9, and it is equals to PL square. PL is 1, therefore PL square is 1 squared, that is 1, plus LQ square. LQ is the missing side, so we leave it as it is. So it is, in total, we shall find out that 9 equals to 1 plus LQ square. Here we subtracted 1 from this equation, and finally found out that 9 minus 1 is 8, equals to LQ square. Here we substituted 8 by 4 times 2, so we got that 4 times 2 equals to LQ square. Here we took out of this equation, and finally found out that LQ equals to the square root of 4, that is 2, so inside the out we left only with 2. So in total we shall find out that LQ equals to 2 times square root of 2 units in itself. In this factorial LQ and M, the opposite sides are equal to each other. That is to say, side LQ equals to the opposite side MN. But LQ equals to 2 times square root of 2, therefore the opposite side MN must be also equal to 2 times square root of 2 units in itself. Okay. This is line 7 MN, that we just found out that MN equals to 2 times square root of 2 units in itself. In the next step, we define this short line 7 MO as A. So ON, the missing line 7 ON must be equal to MN minus MO. ON equals to MN minus MO. So ON equals to MN, MN is 2 times square root of 2, minus MO. MO is A. So in total, ON equals to 2 times square root of 2, minus MN is in its name. In the next step, we join points O and Q together by side line. Point O is the center of this biggest semicircle. Point Q is the midpoint of this chord EF. It is the center of this semicircle. So from the center of this biggest semicircle, that is to say from point O, we draw line segment OQ that bisect chord EF. EF is the diameter of this small semicircle. In total is equals to 2. At point Q, it has been bisected into 2 halves. The first half EQ is 1, the second half F is also 1. And because of the fact that OQ bisects chord EF, OQ will be perpendicular to chord EF. Again, because of the fact that from the center of this biggest semicircle, that is point O, we draw line segment OQ that bisects chord EF. Line segment OQ will be perpendicular to EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. Again, according to Rule 30, whenever you draw a line segment from the center of the circle that bisects a chord, then that line segment will be perpendicular to that chord. OQ bisects chord EF, therefore OQ will be perpendicular to EF. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. So in the next step, we join points E and O together by straight line. EO is the radius of this biggest semicircle, that is X. Then we implement the Pythagoras theorem on this right line EOQ. According to the Pythagoras theorem, in this right line EOQ, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. And again, this triangle EQO, according to the Pythagoras theorem, EQ squared, that is the square of the hypotenuse, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. EO is X, therefore EO squared is X squared, it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared plus QO squared. Again, EQ is X, therefore EO is X, therefore EO squared is X squared, it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1 plus QO squared. What is the value of QO squared? QO is one side of this green triangle EQO, but QO is also the hypotenuse of this pink triangle QNO. And therefore QO squared equals to QN squared plus NO squared. So QO squared equals to QN squared plus NO squared. So in total X squared equals to 1 plus Qn squared. Qn is 1, therefore Qn squared is 1 squared. Plus On squared. On is 2 times square root of 2 minus A, and therefore On squared is 2 times square root of 2 minus A squared. So in total, we found out that X squared equals to 1 plus 1 plus 2 times square root of 2 minus A squared. So X squared equals to 1 plus 1 is 2, we open the brackets of this expression, and remember that 2 times square root of 2 minus a squared equals to 2 times square root of 2 squared, that is 8, plus a squared minus 2 times square root of 2 times 8. So x squared equals to 2 plus 8 is 10, plus a squared, and we have minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times 8. So in total, according to equation 1, actually found out that x squared equals to 10 plus 4 times square root of 2 times 8 plus a squared. This is according to equation 1. We repeat it on the same process that we did on this side of this biggest semicircle, on this side. That is to say, we join points O and P together by side line. Point O is the center of this biggest semicircle. So from the center of this biggest semicircle, we draw line segment OP, then bisect chord CD. Why OP bisects chord CD? Because CD is the diameter of this semicircle, that is equals to 4 in total. At point P, chord CD is has been bisected into 2 halves. The first half CP is 2, the second half PD is also 2. So line segment OP bisects chord CD. And therefore, according to Rule 30, whenever we have a line segment that is going from the center of the circle and bisect the chord, then that line segment OP will be also perpendicular to chord CD. If OP is perpendicular to CD, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to the same rule, Rule 30. So in the next step, we join points O and C together by side line. OC is the radius of this biggest semicircle, that is equals to x. So in the next step, we implemented the Pythagoras theorem on this side line CPO. This side line CPO according to the Pythagoras theorem, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. And again, the right hand CPO according to the Pythagoras theorem, CO squared, that is the square of the hypotenuse, equals to PC squared plus PO squared. CO is x, therefore CO squared is x squared, and it equals to CP squared. CP is 2, therefore CP squared is 2 squared, that is 4, plus PO squared. So again, CO is x, therefore CO squared is x squared, and it equals to PC squared. PC is 2, therefore PC squared is 2 squared plus 4. And we have here plus PO squared. PO is one side of this right triangle PCO, but PO is also the hypotenuse of this pin triangle PMO. Again, PO is the hypotenuse of this pin triangle PMO. And therefore, according to the Pythagoras theorem, if we implement the Pythagoras theorem on this pin triangle PMO, PO squared equals to PM squared plus MO squared. So PO squared equals to PM squared plus MO squared. So in total, x squared equals to 4 plus PM squared plus MO squared. PM is 2, therefore PM squared is 2 squared, that is 4 plus MO squared. MO is 8, therefore MO squared is 8 squared. So in total, we should found out that according to equation 2, x squared equals to 4 plus 8 squared. So x squared equals to 4 plus 4, that is 8 plus 8 squared. This is according to equation 2, and according to equation 1, we actually found out that x squared equals to 10 plus 8 squared minus 4 times square root of 2 times 8. So we have two different equations for x squared. Therefore, we can do equation 3 that states that x squared according to equation 1 must be equal to x squared according to equation 2. X squared according to equation 1 equals to 10 plus a squared minus 4 times square root of 2 times a, and it must be equal to x squared according to equation 2, that equals to 8 plus a squared. So in total, according to equation 3, 10 plus a squared minus 4 times square root of 2 times a equals to 8 plus a squared. Here we have a squared on both sides of this equation, so a squared will get cancelled. After we cancelled a squared, we subtracted 8 from this equation, and we found out that 10 minus 8 is 2, minus 4 times square root of 2 times a equals to 8 minus 8 is 0. So 2 minus 4 times square root of 2 times a equals to 0. Here we get 4 times square root of 2, 4 times square root of 2 times a to this equation, and finally found out that 2 equals to 4 times square root of 2 times a. Here we divided this equation by 2 and finally found out that 2 over 2 is 1 and 4 over 2 is 2, so in total this expression equals to 2 times square root of 2 times a. So in total, according to equation 3, I should find out that 1 equals to 2 times square root of 2 times a. Here we divided this equation by 2 times square root of 2, and I should find out that a equals to 1 over 2 times square root of 2 units. So this is my set MO, this equals to a, and a equals to 1 over 2 times square root of 2 times a. And a equals to 1 over 2 times square root of 2. According to equation 2, x squared equals to 8 plus a squared. So x squared equals to 8 plus a squared. A is 1 over 2 times square root of 2, and therefore a squared must be equal to 1 over 2 times square root of 2 squared, that is 8. So in total, a squared equals to 1/8. So in total, according to equation 2, we shall find out that x squared equals to 8 plus 1/8. So x squared equals to 1/8 and we have plus 8. So we multiply 8 by 8 and then we divide it by 8 in order to have a common factor with this number. So 8 times 8 is 64 and then we divide it by 8, so we change nothing. So in total, x squared equals to 64 plus 1 is 65 over 8. So in total, according to equation 2, we shall find out that x squared equals to 65 over 8. Our task is to find out the size of this shaded region. What is the size of this shaded region? What is the size of this shaded region? From the drawing, it is ready to say that the size of this shaded region in total it is equal to the area of this biggest semicircle minus the area of this right semicircle minus the area of this left semicircle. Read again. The size of the shaded region is equal to the area of the biggest semicircle minus the area of the right semicircle minus the area of the left semicircle. The size of this biggest semicircle, the radius of this biggest semicircle is x, and therefore the area of the biggest semicircle must be equal to pi x squared over 2. Minus the area of the right semicircle, the radius of the right semicircle is 2, therefore the area of the right semicircle must be equal to pi 2 squared over 2. Minus the area of the left semicircle, the radius of the left semicircle is 1, therefore the area of the left semicircle must be equal to pi 1 squared over 2. So we took pi over 2 as a common factor from those two expressions, so inside the brackets we left with x squared minus 4 minus 1. X squared is 65 over 8, minus 4 minus 1 is minus 5. So in total, the size of the shaded area equals to pi over 2 times 65 over 8 minus 5. Here we multiplied minus 5 by 8 and then we divided by 8 in order to have a common factor with this number. And we found out that the size of the shaded area equals to pi over 2 times 65 over 8. We multiplied minus 5 by 8, so minus 5 times 8 is minus 40, and then we divided by 8, so we change nothing. So in total, the shaded area equals to pi over 2 times 65 minus 40 over 8. 65 minus 40 is 25, so in total, in the numerator we have 25 pi over 2 times 8 is 16. So in total, we found out that the size of this shaded area, it is equal to either 25 pi over 16 square units in size. So in terms of numbers, the size of this shaded area is equal to 4.908 square units in its size. So we'll finish to repeat on the solution of the first question. The next step, we repeat on the solution of the second question. In the second question, our task was to find out the size of this shaded region. The shaded region, it is actually this small semicircle, so we have to find out the area of this small semicircle, that is the shaded region. So in the drawing we have two semicircles that intersect with each other. Line segment AM equals to 4 units in its length. This is line segment MN that is also, or chord MN that is also equals to 4 units in its length. This is line segment NB that is equals to 2 units in its length. The diameter AB of this big semicircle equals to in total to 3 plus 3 plus 2, that is 8. And again, the diameter AB of the big semicircle equals to 3 plus 3 plus 2, that is 8. We define the radius of this big semicircle as R. The radius R must be equal to the diameter AB over 2. That is to say it is 8 over 2, that is 4. So if we found out that the radius R of this big semicircle equals to 4 units in its length. We define the center of this big semicircle, this point is point. Also, AO is the radius of this big semicircle, that equals to 4. We find the center of this small semicircle, this point is point S. What is the length of this missing line segment OM? OM equals to AO, that is the radius of this big semicircle, that is 4, minus AM, that is 3. So MO in total equals to AO minus AM. MO equals to AO minus AM. AO is the radius of the big semicircle, that is 4, minus AM, that is 3. So in total, MO equals to 4 minus 3, that is 1. So MO equals to 1 in its length. In the next step, we did the construction, that is to say from the center of this small semicircle, that is to say from point S, from this point S, we draw perpendicular ST on chord MN. Again, from point S, we draw perpendicular ST on chord MN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. According to rule 15, whenever you draw a perpendicular to the chord from the center of the circle towards any chord, it will bisect the chord. So we draw perpendicular ST from the center of this big semicircle, that is point S. We draw perpendicular ST on chord MN. And according to rule 15, perpendicular ST bisects chord MN. If ST bisects chord MN, it means that the first half of MT must be equal, the first half of chord MN, that is MT, must be equal to the second half of chord MN, and each half must be equal to MN over 2, because MN has been bisected. So according to rule 15, perpendicular ST bisects chord MN. The first half MT must be equal to the second half of TN, and each half must be equal to MN over 2. MN is 3, so MN over 2 is 3 over 2, that is 1.5. So the first half of chord MN is MT, that is 1.5, the second half, and it is of course equals to the second half TN, that is also 1.5 units in its length. So what is the length of this? This is 97 OT, or TO. TO equals to TM minus OM. Again, TO equals to TM minus OM. And again, TO equals to TM minus OM. So TO in total equals to TM. TM is 1.5 plus OM. OM is 1. So in total, TO equals to 1.5 plus 1, then 1 half. So this is the short line segment TO or OT, that equals to 1 half units in its length. In the next step, we join points S and O together by straight line. Point O is the center of this big semicircle. This is line segment OS. Line segment OS bisects chord PQ. PQ is the diameter of this small semicircle, that equals to 2x. At point S, the diameter PQ is when bisected into 2 halves. The first half PS is x, the second half SQ is also x. So whenever you have a line segment that is launched from the center of the circle and bisects a chord, that line segment is also perpendicular to that chord. Line segment OS bisects chord PQ, therefore line segment OS must be perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 30. So in the next step, we define the length of line segment SOSY, define the length of line segment STSH. We just write down found out that OT equals to 1 half. So in the next step, I copied the right line SOT in the new equation, implemented the paragraph theorem, and this right line SOT. This is right line SOT that I copied from the original drawing. In this right line SOT, SO squared, that is the square of the hypotenuse, equals to ST squared plus OT squared. SO is y, therefore SO squared is y squared, and it is equals to ST squared. ST is z, therefore ST squared is z squared, plus OT squared. OT is 1 half, therefore OT squared is 1 half squared, this is 1/4. So in total, according to equation 1, we actually found out that y squared equals to y squared equals to h squared plus 1/4. In the next step, we join points S and N together by straight line. Point S is the center of this small semicircle. Point N is the point on the small semicircle itself. Therefore, Sn is the radius of this small semicircle, that is equals to x. In the next step, I copied the right line SON in an equation, we implemented on it, the Pandorus theorem. This is the right line SOT, SNT, that I copied from the original drawing, ST equals to h. We just write down found out that Sn equals to x, and Tn equals to 3 halves. So in this right line S and T, according to the Pandorus theorem, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn is x, therefore Sn squared is x squared, and it is equals to St squared. St is z, therefore St squared is z squared, plus Tn squared. Tn is 3 halves, therefore Tn squared is 3 halves squared, that is 9/4. So in total, according to equation 2, x squared equals to h squared plus 9/4. 16 again. According to equation 2, we found out that x squared equals to h squared plus 9/4. But according to equation 1, we already found out that y squared equals to h squared plus 1/4. We subtracted those two equations from each other, that is to say 2 minus 1. And you got that x squared minus y squared equals to, in this side of the equation, we have h squared plus 9/4. Once this side, then h squared plus 1/4. So x squared minus y squared equals to, open the brackets here, h squared plus 9/4. Open the brackets here. After open the brackets, we have here minus h squared minus 1/4. So x squared minus y squared equals to h squared minus h squared is 0. 9/4 minus 1/4 is 8/4. 8/4 is 2. So in total, according to equation 3, we found out that x squared minus y squared equals to 2. In the next step, we join points P and O together by straight line. Point O is the center of this big semicircle. Point P is the point of the big semicircle itself. Therefore, OP is the radius of this big semicircle. It equals to 4. In the next step, I copied the right triangle PSO in the page and we implemented the Pythagoras theorem. We implemented the Pythagoras theorem on this right triangle PSO. This is right triangle PSO that I copied from the forming. This right triangle PSO, PO squared, that is the square of the hypotenuse, equals to PS squared plus SO squared. PO is 4, therefore PO squared is 4 squared, that is 16, and it equals to PS squared. PS is x, therefore PS squared is x squared, plus SO squared. SO is y, therefore SO squared is y squared. So in total, according to equation 4, we actually found out that 16 equals to x squared plus y squared. So again, actually found out that according to equation 4, x squared plus y squared equals to 16, while according to equation 3, we only found out that x squared minus y squared equals to 2. Then we added equation 4 to equation 3. And actually found out that x squared plus x squared is 2x squared, y squared minus y squared is 0, 16 plus 2 is 18. So then according to equation 5, we actually found out that 2x squared equals to 18. Here we divided this equation 5 by 2, and finally found out that x squared equals to 18 over 2, that is 9. So x squared equals to 9. Our task is to find out the area of this shaded region. The shaded region, this shaded region is the area of this small semicircle. So the shaded region is the area of this small semicircle. The radius of this small semicircle is x, and therefore the area of this small semicircle must be equal to pi x squared over 2. So it is pi over 2 times x squared. X squared is 9, so we substitute x squared by 9. In total, I actually found out that the area of the shaded region equals to pi over 2 times 9. 9 over 2 is 4.5, so in total this expression equals to 4.5 pi. So in total, I actually found out that the area of this shaded region, that is the area of this small semicircle, equals to either 4.5 pi exponents in size, or in terms of numbers, the area of this shaded region is equals to 14.137 exponents in its size. Okay, thank you very much.